Welcome back to the deep dive. Today, we're looking into something pretty critical. Proactive defense against, well, a future threat, quantum computing.
That's right.
Specifically, we're diving into a huge engineering effort by Signal. They've upgraded their protocol to try and withstand what some people have, maybe jokingly, called the cryptocalypse.
It sounds dramatic, but the underlying threat is real.
Yeah, you hear the joke, right? Experts saying quantum computing is always like 15 to 30 years away. And they've been saying that for 30 years.
But the risk isn't just future speculation. The encryption we use now, think elliptic curve, Diffie-Hellman, ECDH, it's everywhere that's vulnerable.
Vulnerable to Shor's algorithm if you have a big enough quantum computer.
Exactly. And the scary part is, if someone builds that computer later, they could potentially decrypt communications they've intercepted and stored today. Everything you thought was private.
Oof. So this is the harvest now, decrypt later problem. Signal's trying to get ahead of that.
Precisely. They didn't want to wait. Their mission was to build in quantum resistance now. They developed this new mechanism, the sparse post-quantum ratchet, SPQR for short.
SPQR. Sure.
And they mixed that with their existing protocol to create what they're calling the triple ratchet.
The triple ratchet.
Yeah.
And the goal was quantum resistance without messing anything else up.
That's the key.
Yeah.
Maintain all the security they already had, keep the user experience the same, which was a massive challenge.
I've heard the original Signal protocol described as like a fine Swiss watch. Really intricate.
That's a good analogy. It was already incredibly complex, very optimized. So trying to weave in this entirely new quantum safe layer without, breaking something subtle or creating unintended shortcuts, it was daunting.
So pulling it off was a big deal.
A huge deal. A real engineering triumph, frankly.
Okay, so before we get into the new SPQR thing, let's quickly recap what the original Signal protocol already did so well. There were two guarantees, right? Forward secrecy and post-compromise security, FS and PCS.
Yes, crucial guarantees. Forward secrecy, FS, means if someone steals your key now, they can't read your past messages. Your history is safe.
Got it. Past is protected.
And post-compromise security, PCS, is about the future. It's the protocol's ability to heal itself. If someone does compromise your session, future messages should become secure again as new keys are exchanged.
Okay, healing. And that healing relied on the original double ratchet.
Correct. The double ratchet is the engine driving both FS and PCS. It has two parts ratcheting forward. One uses symmetric key cryptography, basically hashing, which is thankfully quantum safe.
Okay, one part's fine.
But the other part, the Diffie-Hellman ratchet, relies on those ECDH key exchanges. And that's the part vulnerable to quantum computers.
So that's the weak link for the healing, the PCS part.
Exactly. If an attacker, let's call her Mallory, records all your encrypted traffic today, stores it, waits maybe 10, 20 years for a working quantum computer.
Then Mallory can use Shor's algorithm to break those recorded ECDH exchanges.
Right. And because ECDH is fundamental to how the session heals, breaking it means all future keys derived after that point are compromised. The session never heals from that quantum attack.
That's bad. Didn't Signal already do something back in 2023, PQXDH?
Good point. Yes, they did. PQXDH made the initial handshake quantum resistant, so setting up the conversation became safer against harvest now decrypt later.
But just the setup.
Right. It didn't protect the ongoing key updates, the continuous ratcheting that provides the actual post-compromise security. That remained vulnerable until this latest upgrade.
Okay, so to fix the ongoing ratcheting, they needed to continuously mix in quantum safe keys. They chose something called ML-KEM 768.
Yes, ML-KEM 768. It's based on Crystal's Kyber, which NIST has standardized. It's a key encapsulation mechanism, a KEM, basically a way to securely agree on a shared secret even against a quantum attacker.
So swap out the vulnerable ECDH exchanges with this ML-KEM. Sounds simple enough, but I gather there was a catch. A big one.
A huge one. Data size. This was the core engineering nightmare.
How big are we talking? The old ECDH keys were
tiny, 32 bytes, really small, easy to piggyback on messages without anyone noticing.
Okay, 32 bytes. And the new ML-KEM material.
Well, you need to exchange two pieces, an encapsulation key, or EK, and a ciphertext, CT. Each one is over 1,000 bytes.
1,000 each?
Yeah. Together, the total exchange is 2,272 bytes.
Wow. Okay, 32 bytes versus over 2,200 bytes. That's, what, a 71 times increase?
Exactly. It's massive. Matt Green, the cryptographer, had that great quote he called it the challenge of sneaking an elephant through a tunnel designed for cats.
Perfect analogy. It's not just the size, right? It's doing it reliably when people might be offline, bad connections.
Precisely. Asynchronous communication makes it so much harder. So the naive solutions just didn't fly.
Like what? What did they rule out first?
Well, you can't just send this massive key, say, only once a week or every 50 messages. What if someone's offline for longer than that? They miss the update, the quantum ratchet breaks for them?
Okay, so less frequent updates are out. What about just chopping it up? Send the 2,272 bytes in, like 71 little 32-byte pieces?
Seems logical, right? But that fails too, especially if there's a malicious actor in the middle.
Oh, so?
Imagine Mallory, the attacker, control the network slightly. She doesn't need to block everything. She just needs to consistently drop, say, chunk number 3 of those 71 chunks every single time it's sent.
Ah, so the recipient never gets all the pieces needed to put the key back together?
Exactly. The key agreement never completes. The quantum ratchet is silently broken, and the users might never even notice because it doesn't cause a total connection failure. It's a sneaky denial of service against the security update itself.
Okay, that's a clever attack.
Yeah.
So simple chunking is out, sending less often is out. How did they solve this elephant problem? You mentioned 2 key strategies.
Right. The first was using erasure codes.
Or erasure codes, like for data storage, RAID setups.
Kind of, yeah. Same principle applied to message transmission. Instead of needing all 71 chunks to arrive perfectly, you add redundancy.
How does that work here?
You break the data, say the 1,000 byte EK, into maybe 12 chunks, but design it so the receiver only needs any 10 of those 12 chunks to reconstruct the original EK.
I see. So losing 1 or 2 specific chunks doesn't matter anymore.
Exactly. It builds in resilience against random packet loss, but crucially, it foils that sneaky Mallory attacker. To stop the key exchange now, she can't just drop 1 chunk. She has to block so many chunks, like almost all of them, that it basically becomes a full-blown, very noticeable denial of service attack.
Ah, makes sense. It forces the attack to be loud instead of silent. Okay, erasure codes solve the reliability. But what about the sheer size slowing things down? That 71x increase still sounds like it would lag.
Right. That led to the second innovation, the ML-KEM braid optimization. This was about making these change faster by being clever about the KEM algorithm itself.
Okay, getting into the nuts and bolts of ML-KEM now.
A little bit, yeah. They dug into the steps of the algorithm and found something interesting. Step 3D, generating the largest part of the ciphertext, CT, about 960 bytes. Turns out it only needs a small piece of initial input from the sender, just 64 bytes.
Only 64 bytes triggers the big calculation. That sounds useful.
Extremely useful. So here's the optimization. Alice, the sender, computes her whole encapsulation key, EK, but she first sends just that critical 64-byte piece. Let's call it EK1.
Then it's the small catalyst first.
Right. Bob, the receiver, gets EK1. He doesn't have to wait for the other 1,000-plus bytes of the EK. He immediately uses EK1 to start computing his large 960-byte part of the ciphertext, CT1, in the background.
While he's computing that, Alice is sending the rest of her EK.
Exactly. Alice sends the remaining bulk of her EK, let's call it EK2, in parallel, while Bob is busy computing CT1. Then Bob sends his much smaller CT part, CT2, back.
So the required sequential parts, EK1 going one way, CT2 coming back, are kept really small, just a few chunks.
Minimal. 2 chunks for EK1, 4 for CT2, using their chunking system.
And the big data transfers the rest of Alice's EK2, 36 chunk, and the bulk of Bob's computed CT1, 30 chunks, can happen kind of simultaneously, or at least overlapped.
Pretty much.
Mm.
It maximizes parallelism, makes the most of the limited bandwidth available in each message packet. It's a really clever way to handle the size without introducing huge delays, like braiding the communication together.
That is pretty neat. But did speeding things up cause other problems? You hinted at something?
It did. It immediately raised a subtle but critical issue, security timing. It led to what they called a meditation on how faster isn't always better.
Faster isn't better. How can making the quantum key exchange faster be bad for security? Seems counterintuitive.
It does, right. But think about when the security guarantees kick in. The problem arises if Alice generates new key material too quickly, sort of getting ahead of herself.
Like she sends the stuff for the next key exchange before the current one is even fully confirmed.
Sort of, yeah. Imagine she generates the secrets for the next 3 key exchanges, epochs, in advance. Let's call them derivation keys, DK-check1, DK-check2, DK-check3. She hasn't used them yet. They're just sitting there waiting.
Okay, she's prepared for the future.
But what if Mallory compromises Alice's device right now? Mallory gets access to those 3 unused future derivation keys.
Ah, so the messages that would have been protected by DK-check1, #2, and #3 are now vulnerable because Mallory grabbed the keys before they were even committed to the conversation.
Precisely. The faster you generate these future secrets in parallel, the larger the window of vulnerability if a compromise happens at that moment. Their simulation showed that while parallel generation completed security epochs faster, it paradoxically made more potential future messages vulnerable to a single point-in-time compromise.
Wow. So they had to find a balance fast enough, but not too fast.
Exactly. They had to carefully tune the protocol to balance the speed gained from the braid optimization against minimizing the number of uncommitted future secrets exposed at any given time. It's a really subtle trade-off.
Okay, so managing the size with erasure codes, the speed with the braid optimization, and the timing risks. That brings us to the final system, the triple ratchet. What does that architecture actually look like?
It's actually quite elegant conceptually. Instead of throwing out the old, well-understood double ratchet,
They kept it.
they kept it. They run the battle-tested double ratchet, providing classical security guarantees, and the new sparse post-quantum ratchet, SPQR, for quantum security, side by side in parallel.
Two ratchets running at once.
Yep. Then, the secret keys derived from both ratchets are fed into a key derivation function, or KDF.
And that mixes them together.
Right, it mixes them to produce a single, final, hybrid session key that's used for the actual message encryption.
Okay, that's clever. What's the security advantage of doing that rather than just using the new SPQR?
It's significant. An attacker now has to break both the traditional elliptic curve crypto and the new post-quantum crypto, ML-KEM, to compromise the final key.
So it's stronger against either type of attack.
Exactly. As one researcher, Charlie Jacome, noted, this approach effectively doubles the security, even for people who aren't worried about quantum computers yet. If a flaw is found in ECDH later, ML-KEM still protects you. If somehow a flaw is found in ML-KEM, ECDH still protects you. It's belt-in suspenders cryptography.
That makes a lot of sense. An immediate security boost for everyone. Okay, but rolling this out, how do you update millions of users who might have different app versions, might be offline, without breaking everything?
That required what they called a heterogeneous rollout strategy. The key was designing the protocol to handle mismatches gracefully, especially at the very start of a session.
How does that work? Say I have the new app, but you have the old one.
So you, with the updated client, send your first message. It includes the normal double ratchet stuff plus the new SPQR data. I, with the old client, receive it, but my app doesn't understand the SPQR part, so I just ignore it. I then reply, using only the old double ratchet protocol. When you receive my reply and see it's missing the expected SPQR components, your client says, okay, this person hasn't updated yet, and it temporarily downgrades this specific session to just use the double ratchet.
So it falls back to the old standard if needed. But wait, couldn't our attacker, Mallory, just interfere? Could she just strip out the SPQR data from my first message to force a downgrade, even if you do have the new client?
Excellent question. That was a critical attack vector they had to prevent.
How'd they stop it?
The SPQR data isn't just sent naked, it's emacid.
Yeah.
It has a message authentication code tied to the overall message authentication, meaning Mallory can't remove or tamper with the SPQR data without also invalidating the authentication tag for the entire message. If you, Bob in this case, receive a message where the SPQR data is missing but the authentication fails, your client knows something is wrong, flags the session as compromised, and essentially stops communication or alerts the user.
Gotcha. So Mallory can't silently force a downgrade without getting caught by the message authentication. That's clever.
It ensures the downgrade only happens honestly when one client genuinely hasn't updated yet. And the plan is, eventually, once rollout is near complete, they'll flip a switch to require SPQR and archive old non-SPQR sessions to ensure everyone gets the full protection.
This sounds incredibly complex. All these interacting parts, state machines, potential edge cases with timing and networks. How do you even prove something like this is secure?
You can't just rely on testing. For something this critical, you need formal verification. And Signal made this a core part of the design process from the start, not just an afterthought audit.
Right. They worked with academic researchers, PQ Shield, ASD, NYU.
Yes, top people in the field. They use specialized tools, like Profref, to actually model the protocol mathematically.
What does modeling it do?
It lets you formally prove that the protocol satisfies specific security properties like forward secrecy, post-compromise security, even under adversarial conditions. It's especially good for reasoning about complex state changes, like in a ratchet.
Okay, mathematical proof is good, but does the proof match the actual code people are running?
That's the other, maybe even more impressive part. They use a tool called HACS that automatically translates their production Rust code implementation into a formal verification language called F.
translates the actual code.
Yes. And they run this translation and verification check on every single code change they make as part of their continuous integration CI pipeline.
Wow. So every time a developer pushes an update, the system automatically tries to generate a machine-verified proof that the code still meets the security guarantees.
Exactly. It ensures the implementation rigorously matches the formally verified model. It helps guarantee the app is panic-free, as they put it, meaning certain types of critical errors are proven impossible. It keeps the quality high dynamically.
That's an incredible level of rigor. So the TLDR for the average Signal user
It's
is...
pretty much what Signal aimed for. Our biggest hope is that you never even notice or care. All this complexity, the erasure codes, the braid optimization, the formal verification, it's all engineered to work seamlessly behind the scenes, keeping bandwidth low and making it really hard for an attacker to disrupt things without causing a very obvious outage.
Okay, wrapping this up. It seems like there are two big takeaways here. First, this hybrid approach, the triple ratchet, gives an immediate security boost today, right? It's not just about future quantum computers.
Absolutely. Running both ratchets in parallel provides redundancy. You're protected by both classical and quantum-resistant crypto simultaneously. That's a concrete win right now.
And the second takeaway, this whole effort shows that it is possible for major infrastructure to tackle these huge future threats proactively without breaking the user experience.
It really sets a benchmark, which leads to maybe a final provocative thought for you to consider.
Okay, let's hear it.
We mentioned Signal's success here, but the broader context. Our sources indicate that less than half of Cloudflare's network traffic uses quantum-resistant connections. Only about 18% of Fortune 500 company networks support it. There's a lot of, well, industry-wide lethargy, let's call it.
So Signal managed it for their complex messaging app.
Right. If they can pull off this transition for millions of users in a highly asynchronous, complex environment, what does that say about, say, government systems, global financial networks? These systems often move much slower, and the upgrades are incredibly expensive.
So the question is, if Signal can do it, why aren't others moving faster?
Exactly. What critical secrets, government, financial, personal are being harvested right now, sitting on servers somewhere, just waiting for that quantum future, because organizations are dragging their feet on making the necessary and, yes, difficult and costly upgrades. How long can they afford to wait?
A sobering thought indeed. Something to definitely mull over. That's all the time we have for this deep dive.